Buried in the lunar regolith, the fine dust covering the moon's surface, lies an isotope so rare on Earth that the entire planet contains less than 15 kilograms. Yet the moon may hold over 1 million metric tons. Helium-3, a lightweight isotope of helium with 2 protons and 1 neutron, could theoretically fuel fusion reactors without producing dangerous neutron radiation or long-lived radioactive waste. The concentration reaches 20 parts per billion in some lunar soils, 10,000 times higher than anything found on Earth. In this video, we'll examine how scientists discovered helium-3 on the moon, what mechanisms concentrated it there over billions of years, and what significant obstacles stand between detection and extraction. For decades, fusion energy has remained approximately 30 years away, a timeline that has persisted since the 1950s. Traditional deuterium-tritium fusion, the most researched approach, requires temperatures exceeding 100 million Kelvin and produces high-energy neutrons that damage reactor walls and create radioactive waste with half-lives of decades. The tritium fuel itself must be bred from lithium using those same neutrons, creating a dependency on neutron capture that limits reactor efficiency. Before lunar exploration, scientists understood that helium-3 existed primarily in stellar interiors and was ejected in solar wind, charged particles streaming from the sun at speeds around 400 kilometers per second. Earth's magnetic field deflects this solar wind, preventing helium-3 accumulation in terrestrial materials. The moon, lacking both magnetic field and atmosphere, presents a fundamentally different environment. The initial detection came from Apollo mission soil samples returned between 1969 and 1972. Apollo 11, 12, 14, 15, 16, and 17 collected 382 kilograms of lunar material from 6 different landing sites across the near side of the moon. Researchers at the University of Wisconsin-Madison, led by fusion researcher John Santarius and physicist Gerald Kolsinski, analyzed these samples throughout the 1980s and 90s. More recently, instruments aboard the Lunar Reconnaissance Orbiter, launched in 2009, mapped variations in regolith composition across the entire lunar surface. China's Chang'e missions, particularly Chang'e 5, which returned samples in 2020, provided additional data from the Oceanus Procellarum region, an area suggested to contain relatively high helium-3 concentrations based on titanium content correlations. Apollo samples underwent mass spectrometry analysis, which separates atoms by their mass-to-charge ratio. The process involves heating lunar soil to temperatures exceeding 800 degrees Celsius in a vacuum chamber, releasing embedded gases including helium isotopes. Researchers then measured the ratio of helium-3 to helium-4, the common isotope with 2 neutrons instead of 1. The Lunar Reconnaissance Orbiter employs the Diviner Lunar Radiometer experiment, which measures thermal emission in 9 spectral channels. While Diviner cannot detect helium-3 directly, it maps surface temperatures and identifies areas with high titanium oxide content in soil. Studies have noted a correlation between titanium-rich soils and helium-3 concentration, though the relationship remains incompletely understood. The mechanism may involve titanium's crystalline structure more efficiently trapping solar wind particles, but this interpretation requires further investigation. The key limitation: all measurements represent tiny sample sizes or indirect correlations. No instrument has directly measured helium-3 distribution across large lunar areas. Apollo samples showed helium-3 concentrations ranging from 1.4 to 50 parts per billion by weight, depending on location and soil maturity. Mare regolith, the dark volcanic plains, generally contained higher concentrations than highland samples. The correlation with soil maturity was particularly significant. Older, more weathered soil exposed to solar wind for longer periods accumulated more helium-3. Grain size also mattered. Fine particles with diameters under 20 micrometers showed higher concentrations than coarser grains, consistent with greater surface area exposure to solar wind implantation over geologic time. The top few meters of regolith contain most accessible helium-3, with concentrations decreasing rapidly below 2 to 3 meters depth. Extrapolating from Apollo data and LRO mapping, researchers calculated that approximately 1 million metric tons of helium-3 might exist in the lunar regolith, primarily in Maria regions where titanium-rich basalts were exposed to billions of years of solar wind. 1 metric ton of helium-3, theoretically, could produce energy equivalent to approximately 50 million barrels of oil, though this calculation assumes functional fusion reactors that don't yet exist. Scientists have proposed several frameworks for understanding helium-3 as a potential energy resource, each with distinct implications. One interpretation considers direct mining operations, processing approximately 150 million metric tons of regolith would theoretically yield 1 metric ton of helium-3. The energy expenditure for heating soil, extracting gases, and separating isotopes represents a significant fraction of the potential energy return. Calculations suggest anywhere from 15 to 40% of output energy consumed in the extraction process itself, depending on mining efficiency and thermal management. Another model focuses on deuterium-helium-3 fusion reactions. This approach requires even higher temperatures than conventional deuterium-tritium fusion, around 1 billion Kelvin compared to 100 million Kelvin. The advantage: the reaction produces primarily charged particles, protons, rather than neutrons, allowing direct conversion to electricity through electromagnetic induction. Researchers at Princeton Plasma Physics Laboratory have modeled reactor designs specifically for deuterium-helium-3 fuel, though no experimental demonstration has achieved net energy gain. A third interpretation emphasizes lunar industrial infrastructure development. Mining helium-3 requires massive-scale operations, excavating, processing, and refining billions of tons of material. Some researchers propose this infrastructure could support broader lunar resource utilization, including oxygen extraction from regolith for life support and propellant production, making the economics more favorable than helium-3 extraction alone. This data does not confirm economic viability or technological feasibility. Several critical limitations exist. First, fusion reactors using helium-3 do not currently exist beyond conceptual designs. ITER, the International Thermonuclear Experimental Reactor under construction in France, focuses on deuterium-tritium fusion, a less demanding fuel cycle than helium-3 reactions. No experimental facility has demonstrated sustained deuterium-helium-3 fusion with net energy gain. Second, the energy cost of lunar mining operations remains highly uncertain. Transport costs to the moon currently exceed $1 million per kilogram. Extracting and returning even 1 metric ton of helium-3, requiring processing approximately 150 million metric tons of regolith, would cost trillions of dollars at current launch prices. Proposed reductions through reusable spacecraft and in-situ resource utilization are theoretical. Third, the helium-3 distribution may be less uniform than simple extrapolations suggest. Solar wind flux varies significantly across the lunar surface, depending on magnetic anomalies, localized magnetic fields generated by ancient magnetized crustal rocks. These anomalies could create helium-3 cold spots, where solar wind particles were deflected, making some apparently promising areas uneconomical to mine. Fourth, while the deuterium-helium-3 reaction produces fewer neutrons than deuterium-tritium fusion, it does not eliminate neutron production entirely. Side reactions between deuterium atoms, which occur inevitably in any deuterium-containing fuel mix, still generate significant neutron flux, requiring shielding and creating radioactive materials. Earth's helium-3 occurs primarily in natural gas deposits, where primordial helium from planetary formation became trapped in underground reservoirs. The concentration reaches approximately 7 parts per trillion in some natural gas fields, roughly 3,000 times lower than lunar regolith. Global terrestrial helium-3 reserves may total only 10 to 15 kilograms, compared to the estimated 1 million metric tons on the Moon. Jupiter's atmosphere contains vastly more helium-3, potentially trillions of metric tons based on spectroscopic measurements of the planet's composition. However, Jupiter's gravity well requires energy exceeding current propulsion capabilities by orders of magnitude, and the planet's radiation environment, intense magnetosphere, and lack of solid surface make extraction operations far more challenging than lunar mining. Regarding alternative energy sources, terrestrial solar installations and wind farms represent more immediately deployable technology. A single large solar farm covering 100 square kilometers in optimal locations can generate approximately 500 megawatts continuously, roughly equivalent to the theoretical output from burning 40 kilograms of helium-3 annually, but without requiring fusion reactor development or lunar mining infrastructure. The scientific significance extends beyond energy production possibilities. Understanding helium-3 distribution provides direct evidence of solar wind flux variations across billions of years. Changes in concentration with depth reveal solar activity patterns during different epochs, offering a geological record of the Sun's behavior that Earth's protected surface cannot preserve. Lunar regolith analysis also demonstrates broader principles of space weathering, how airless bodies accumulate volatiles over time. This mechanism operates on asteroids, Mercury, and other atmosphereless bodies throughout the solar system. Developing techniques to extract embedded gases from regolith advances our understanding of resource availability beyond Earth-Moon space. From an engineering perspective, large-scale lunar mining would require solving fundamental challenges in remote operations, autonomous systems, and in-situ manufacturing. Whether or not helium-3 proves economically valuable, the infrastructure development necessary to attempt extraction would establish capabilities applicable to asteroid mining, Mars base construction, and deep space missions requiring local resource utilization. The geopolitical dimension matters as well. Multiple nations, including the United States, China, Russia, and India, have referenced lunar helium-3 in space policy documents. While international space law, specifically the Outer Space Treaty of 1967, prohibits national sovereignty claims over celestial bodies, it does not clearly address resource extraction rights. Establishing precedents for lunar mining could influence frameworks governing all extraterrestrial resource utilization. The Moon's helium-3 deposits represent a verified resource whose value depends entirely on technologies that don't yet exist. Whether fusion reactors achieve commercial operation, whether lunar mining becomes economically viable, and whether helium-3 proves superior to alternative energy sources remain open questions requiring decades of development. What we can observe: the isotope exists in measurable quantities, concentrated through billions of years of solar wind implantation in an environment Earth's magnetic field prevented from forming terrestrially. The mechanisms that created this resource continue operating today, adding approximately 50 kilograms of new helium-3 to the lunar surface annually. If you found this examination of lunar resources valuable, consider subscribing for more scientifically grounded explorations of space phenomena. What other aspects of lunar science would you like to see investigated? Share your thoughts in the comment. All visuals in this video are illustrative and created for educational purposes, based on proposed engineering concepts discussed in scientific research and official space agency publications.